All right, we're in part 2 video. I actually wanted to go over this last one we left here. That Joe is running on a circular track with a diameter of 100 feet. If he runs at a constant speed of 4 feet per second, what's his rate in radians per hour? And I'm actually going to show you two different ways to do this problem. So the first was kind of how I left it, all right, is that his speed is 4 feet in 1 second, so 4 feet per second. And our goal in the end, and you can kind of see the answer here, is radians and per hour. Okay, first feet into radians. We have to turn feet into radians. Feet don't go, aren't a good conversion really quickly into radians. But what we can do is we can turn feet into a revolution. So one revolution all the way around this circular track, if the diameter is 1,000 feet, the radius is 500 feet. All the way around the track, and I actually have this the wrong way. I actually want the revolution. I have to do this the wrong way. I want the revolution on the top. Sorry, guys. So I want 2 times pi times 500 feet is the circumference, all right, the distance around this track. And that means it's 1 revolution. Well, we know that 1 revolution is really 2 pi radians. Okay, and we have to change seconds into hours. And we know that 1 hour is really 3,600 seconds. That's how many seconds are in an hour, in case you're wondering. All right, seconds. So here, I see some things that we can reduce. We can reduce the 2 pi radians here, okay? And what it turned out to be 4 times converting the seconds, and we're dividing by here the radius. So we really kind of took 4 and divided by the radius times the seconds. So when we work that out, we actually got to grab my calculator here, sorry. When I work that out, I have the answer here, 28.8 radians per hour. That's how we got the radians. Well, we can kind of change this, and we can talk about this angular displacement. Means how much did we change? The angular displacement, we're going to see a few problems like this, saying if we went 2.3 revolutions, and we kind of have done this before. We said, okay, if you went around 2 times and then 0.3 more, how many radians is that? Well, we did it when it was degrees, and what we did is we just took the number of revolutions and we multiplied it by 360. Same concept. We're going to take 2.3 here, and we're just going to multiply it by how many radians, 2 pi radians that are in a circle, okay? So our answer here is 2.3 times 2 pi, and it turns out to be 14.4 radians. So I just took 2.3 times 2 times 3.14. So we always use 3.14. So that's our displacement. That's what's called our displacement, how far we went in radians. Again, we're going around and around. Anything more than 2 pi, or 2 pi is more than a circle. Angular velocity. So the angular velocity is the velocity that as your angle is changing as you're going around the velocity. So usually velocity is considered in a straight line. You're kind of consider it in a straight line. Angular velocity says that we're going kind of around in a curved pattern, in a circular pattern here. Angular velocity, this formula is only useful if you have your theta, if your angle given is in radians. So sometimes we have to calculate, we have to change the angle into radians, okay? So let's start here. Find the angular velocity of 3.4 revolutions if those are completed in 6 seconds. Round this to the nearest tenth. So what we could do is we could say, well, 3.4 revolutions is really 2 pi. When I multiply it by 2 pi, I get 21.4 radians. This is my angle, my theta. This is how many times I'm going to go around. And then my formula here says I just have to divide that by how much time it took. Okay, well, my 21.4 radians took 6 seconds. All right, so we have radians, and we're going to find it per second. So we got for an answer here 3.6, and we write our answer as radians per second. All right. The reason I'm kind of like, we kind of do this, we actually just did some of this. We just did, and I got to find more space here. we just did a problem like this where before we might have said 3.4 revolutions in 6 seconds, and we wanted in the end radians per second. Oh, 1 revolution is 2 pi radians. Okay, and really that's what we did. We took 3.14 times 2 pi, and we took 6 and we divided it by 6, and we get the same answer. I kind of like thinking about it like this, but I want to show you the formula because you're going to see this formula in a physics class or perhaps in other classes, or you might even, it won't show up in the ACTs, but you're definitely see it in our book. It comes up in our book. I like thinking of it more like this in conversions, but know that that's where they get the formula from. Same thing. Okay, now we have some Greek letters. If you ever get into to the Greek system, like a fraternity, you're going to need to know all the Greek letters. We're going to be using this letter omega. You might see we always use a lot. We use, what do we use a lot? Theta. We're going to be using a lot. But now we're going to be using this omega a lot too. So I just kind of wanted to show you this Greek alphabet. It's kind of cool. But now we have this velocity, and that's what we just saw was omega, is our angle divided by our time, and that's the same thing as our radius, or the velocity involves the radius now. All right, so velocity is how much it's changing compared to the radius. The idea is, all right, we have a circular track here, and we have a circular track around it. If someone's running here, and they get to this point, at the exact same time this person gets to this point, you know, who ran faster? Well, the person on the outside track ran faster because they had farther to run. And so this involves the idea that we have linear velocity, kind of switching this angular velocity to what if they were just going straight? What if they just had a straight path that they were running and we had to figure out who is going faster, or we have to figure out what is their speed. So find the linear velocity of a point rotating at an angular velocity. So angular velocity, if you remember, was our alpha, or our theta, our degrees, angle degree over the time of 17 pi radians. And if you remember, that's our omega. That's what I was trying to think here, omega. And at a distance from 5 centimeters. And really, our velocity is our radius times our omega, our angular velocity. So if we just follow the formula, we're just here taking 5 times 17 times pi. And we got 266.9 centimeters per second. Okay. So let's look at this. Look, these are some of the word problems. Now here, with the word problems, there's angular velocity problems in here. There's going to be linear velocity problems. You can treat them all like conversion problems. All of these really can be solved with conversion problems. So I'm going to do a couple with you. A wheel turns through 10 revolutions, and how many radians does it turn? It didn't say in any time. So all we need to do is we need to go from revolutions to radians by multiplying by a fraction. So we can think of it as 10 revolutions over 1. Radians, well, 1 revolution is 2 pi radians. Is it that easy? Yep, it's that easy. So this was that angular displacement we did, all right? And so our answer here is 20 pi radians, or you could, oh, I don't have my calculator here to go 20 times 3.14. I should know that in my head. I'm too tired. 3.14. Okay, it's 62.8 radians. Notice how I'm not using pi on my calculator. I'm always using 3.14. I want you to do the same. Now let's look at this one. Now we have 200 revolutions per minute in a minute. We want to know radians per second. So let's deal with revolutions first. Revolutions to radian, 1 revolution is 2 pi radians. Okay, seconds to minutes. 1 minute is 60 seconds. All right, I need to move everything. Oh, not that. Let's do this. That's what I need to move. Let's see if I can move this first. Let's move that over. Let's move that over. Okay, now I have space. And so my answer here in the end is going to be, I need to get my calculator and take 200 times 2 times 3.14 and divide it by 60. My answer is 20.9333, and that was radians per second. Good luck, and the answer key is on the website.